Okay, I'm going to go through and talk about problem 5.32. It's a DC circuit and it has 9 resistors in it and a current source. Okay. Now, one of the things you have to recognize here is that sometimes you'll see like a current source or listed as a voltage source. They're both power sources, so they both types, whether it's a battery symbol or a DC voltage symbol, or a current source like this, they're both power sources, mean they both provide voltage and current. The difference is that when you have it listed like this as a current source, what it means is that it always provides this amount of current, no matter what resistive network is connected to it. Okay. And a voltage source, what that means is it always provides the given value of voltage, no matter um, what resistors are connected to it, no matter what current it provides. Okay. Now, I'll go through and I'll follow along and discuss the approach or the way that the author went through and solved this problem. Of course, there are other techniques you can use and other approaches. You can apply KVL and KCL in different fashion to come up with the same result. Okay. All right. So first part is here's the diagram the author used to define it, and the author chose to solve it by defining this node at the top here and a loop. And so this is applying KCL. Whatever's current coming in is equal to whatever current leaves, the summation of the currents leaving. Okay, that's going to be equal to 0. So whatever's coming in minus whatever's leaving is equal to 0. Um, you can think about this similar to like a water analogy. Like if you have, 1 gallon per minute coming through some pipe, the summation of whatever's coming in, that rate of whichever water's coming in, is got to be the same as the whatever's leaving, right? So if this is coming in 1 gallon per minute and it's a pipe, it has to leave. If you sum these three together, those total have to be 1 gallon per minute. Okay. Now, an electrical circuit, we don't say gallons per minute, we say coulombs per second or amperes, okay, which essentially is what's considered to be charge carriers. So it's a quantity of charge carriers going past a certain point or cross sectional area per second, okay, but it's the same idea. Current is a flow, okay, just like water is a flow, water flows, okay, or molecules of water flow past a certain point is the analogy is with electrical circuits is just that it's charge carriers past a certain point or cross-sectional area per unit time. All right. All right. So a few things here. One is all current sources ideal. Resistance to the wires is negligible, and the resistances of the resistors are constant, meaning they're not changing. Current source is ideal. That just means it's always providing this value, and there's no resistor that's part of this, no resistance. In reality, there is an internal resistance, but in this case, there's none resistance. So this is an automatic one. Also, connecting wires, the resistance usually is electrical resistance of wires is so small that you can neglect it and just say it's 0. And the last one is, yeah, all resistors are constant. So any of the circuits that we work with in this class are all going to be, are going to be the assumptions. Okay, the governing equations. Of course, we have Ohm's law, which just relates the voltage drop across some resistor or combination of resistors. The voltage drop is equal to um, the resistance times the current. Okay. Now, when we're talking about KVL or applying KVL, what we're saying is if you go around the loop, you sum all the voltage, it's going to be 0. So if we think about this like a water analogy, maybe this is a pump that, if it's a water circuit, maybe this is a pump and it pumps water up to a higher elevation. Water flows down, flows down, flows down, flows down, and gets back to that initial point where we started from. What we would say is the energy stored essentially in the water will sum to 0. When you give it energy, loses energy, loses energy, loses energy, loses energy, loses energy. And when you get back to this point, you now have essentially zero energy associated with that water. Okay? If we made this kind of our reference point. All right, so same thing with electron or with voltages in electrical circuits. You give energy to the electrons. They lose energy when they go through resistors, lose energy, lose energy, lose energy, lose energy, and you get back to zero energy state. Give it energy, lose it, lose it, lose it, lose it, lose it, lose it. So what happens is that when you have a voltage source like this, you increase the energy. So this is a plus voltage. When current goes through resistor, you get a drop. So it's a minus voltage, minus voltage, minus voltage, minus voltage, minus voltage, and you're back to zero. Now this works any loop. So if you go up through here, I can do this loop. It comes out to be zero. Or I could go around here. That's also zero. I could go around here, let's say. That's also zero. Even internally here, I can go around here and go around here. And that'll also be, the summation will be zero of the voltages. Okay? So the one the author chose to do is just use this loop right here. Come up with equations for this node. Come up with equations for this loop. And with those two, you can solve those two independent equations. You can actually solve for the unknowns and solve this circuit completely. Okay? All right. So here's our equations. Here's Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. All right. Now the author chose to assign these subscripts for these particular resistors. You know, you may or may not have done the same, but that's basically it. Just basically labeling those resistors. All right. So the first thing we'll do is we're going to do KVL. I'm sorry, not KVL, KCL. And we're just going to start with this node. Positive current coming in, negative leaving, negative leaving, negative leaving. Okay? So we write that equation. I1's coming in, minus I2 leaving, minus I3 leaving, minus I4 leaving. Okay? Well, we know what I1 is. This resistor is in series with a source. Whatever rate electrons are flowing through here, or charge carriers are flowing through this, is the same as it's flowing through this one. Okay? And then it splits some way, but at least it's the same here. Also, what we'll note is that as current goes down through here, it comes through this one and this one together, they come back together and go through here and come back into the source. So right off the bat, we know, 200 milliamperes through there and 200 milliamperes through here. We don't know what these are just yet. Or we don't know what these currents are here, here, and here just yet. Okay? Okay. So now what we'll do is we'll just take this value here. I'm sorry, we already shifted it over. Move the value I1 over to the other side of the equation, reverse all the signs. So what we're saying is whatever's coming in essentially is equal to whatever's leaving. Right? Now the next thing to do is write these currents in terms of voltages. Okay? So what we recognize here is, so first thing we'll do is define these VA and VB as just the voltage drops across these resistor networks here. Okay, so what we're saying is VA is from this point to this point. Since they're in series, we could just add the three together and to come up to and apply Ohm's law to come up with that voltage, right, or that current. And then VB will be from this point to this point, which essentially is, if you look at it, this and this one to get together, and these two are connected together. So the combination of the voltages on these two is going to equal this one. All right? So we rewrite these currents, we apply Ohm's law. We have VA over the current I2, which is the current going through here, is equal to essentially the voltage drop from here to here, divided by the three resistors. Okay? So we write as VA over R2 plus R3 plus R4. And then the other one, VB, which was voltage from this point to this point, divided by these two resistors. Okay. And we write that VB. And then the last one is just VA over R8, which is 4, which is just the voltage from this point to this point. Right? So the voltage drop across the resistor divided by the resistor is equal to the current going through it. Right? So the other part of it I discussed earlier, saying that, well, we find that the voltage drop across these two resistors together is equal to the voltage drop across R8 because this node and this node are shared by the two. Okay, so the voltage drops have to be the same. So when they have common nodes, the voltage drops across devices has to be the same. Okay, so then we just rewrite this as we say VB is equal to V8, so we write it in terms of VB. So now we have one equation and we have these two unknowns. All right, so we need to come up with another equation in order for us to solve for one of these. Then we can, of course, we can solve for the other one. So we need a second equation. All right, so what the author chose to do was find the total resistance of the circuit, or the equivalent resistance, and then determine the source voltage from that. And the reason to do that is we're going to apply KVL around that loop. So if you remove this source, look from the resistance looking in from this point relative to this point, you come up with the equivalent resistance here of this circuit. What you're going to find is it's 17.22 ohms. Sorry. Okay. And then what we can do is find the source voltage. Because essentially when you do that, what happens is that now you have a simple series circuit with a current source and one resistor connected to it. All right. And so we can find the voltage drop across that equivalent resistance. And when we do that, it comes out to be 3.444 volts. Okay. Now what we'll do is we'll apply KVL on that loop, which essentially says source voltage, which is the voltage of this across this device, which is this goes up by a voltage. So this is plus voltage. Then we're going to go down by a voltage here. So voltage across this 7 ohm resistor. And then we already know this is VA from this point to this point. That was defined. So we're going to go up, then we go down, so it's negative. Then we go down by VA, which is negative. And then we go down by one more voltage here, the voltage drop across this, our 1 ohm resistor, which is R9. All right. So what do we have? KVL, VS minus whatever's V1 minus VA, which is the voltage across those three resistors together, minus V9. Okay. Now what we'll do is we'll write those to solve for VA. Pull VA over here. And we know what VS is. And we also know what I1 is. I1 is essentially just the current coming out of that source, right? So the voltage drop across that R1 is just going to be, the 7 ohm resistor, which is going to be the current going through it times its resistance. And the same thing with the 1 ohm resistor. It's going to be current going through it times that resistor, okay? Because what we already said previously was that whatever current's going through here, since this is in series, is the same. So we already know what this is, 200 milliamperes. And like I said before, this one also is 200 milliamperes. So really, we just have current going through these three, which is just this I2 that we can solve for. All right. Okay. Oh. Which we don't need to solve for. We're just going to find the voltage directly, and then we can solve for the current. All right, so then we can solve for VA, just plugging into this equation, the KVL equation. And then we can take that. Once we have VA, we can plug back in and solve for VB. Right? So what it means essentially is going back to this equation, plugging in for VA, algebraically manipulating this equation, then you can solve for VB. Okay, so now we have VB and VA, which is voltage from here to here, and voltage from here to here. And which is the same, of course, from here to here. So what you'll recognize is now, if I know the voltage from here to here, I can solve for that I2. And the same thing here for VB. I can solve for I3. And then, of course, it's the same voltage here to here as the one from here to here, so I can solve for I4. And then one more thing we recognize here is that if I I3 comes into this node and I4 is coming into this node. If you add these two together, it's the same as whatever is going through this resistor. All right. So we go back down. Then we just apply, we solve for I2, just VA over R2 over R3, because it's the voltage drop across the three resistors. That's 46.1 milliamperes. Then we can solve for I3, VB over these two resistors. And then we can solve for I4, which is 118 milliamperes. Okay, because the same voltage here, right? Here's my VB. This is my VB, which is VA. Okay. Then what we can do is add these two together, and then we can solve for the current through R7. Right? Now that we know the currents through all of the resistors, we know these currents, we know what I1 is. We know I1, this is I1 also. We know all these currents, and we know all the currents here, currents through here, and a current through here. We can use those currents, multiply them times the resistors, and we can solve for our voltages. So V1, V2, V3, V4, V5, V6, and V7, V8, and V9. Okay, so that's all it was. Just plugging in those currents, multiplying times the resistors, and you can solve for those. No errors detected, and like I said, this is how we figured out what R7, what the current through R7 was, and the current through R9. Okay, no errors detected. So how do you check? Well, you can do a couple of other things to check to see if it's valid. What you can do is you could do like, you could do KCL here. Let's say this one plus this one's got to be equal to whatever this is, right? We already did the one here, which we checked. You could also do like a KVL around some other loop. So if you go up, so if we go in the opposite direction, it's actually a voltage rise. So we're going up by VB. So you could do I3 times this to give you the voltage drop rise. In this case, it's a rise if you're going from negative to positive. If you're going in the opposite direction, so you're going to say if you add this one together, the voltage drop or voltage increase on this one, and the voltage increase on this one, and subtract it by the voltage decrease here, then you'd find that equals 0, so that loop would be valid. Okay, so you can do any of those. Like I said, you can apply KCL or KVL, and you might want to check a couple of them to verify that it is correct. Okay, and let's see, and that is about it for this one. Of course, there's other ways of going about it, how you could solve it. You could have multiple KVL equations to solve it if you want. You could do some combinations of resistors along the way to make it a little simpler if you want. You could come up with like equivalent resistance to these three, maybe equivalent resistance to these two or something. And then, make your solution a little bit simpler. Or just follow the author's way where they kind of just added them together in the equation. And going down to the bottom here. And that's about it for this one.